No, I think he left.
Never mind. So as I said, this lattice, we can go to dimension up to fourth order. But besides that, G is the same G regardless of their neighbors. And now, John, what I meant before, if I wanted an isotropic substantial, I would be a Gx and Gy. I could probably even give a different G to any direction. I don't know what I would get at that time. You can give random G's. People have not played much with that one. We did Gx and Gy for the ferrofluid. It was good enough, but I mean, we are not really working with ferrofluid, so it was just for fun. So if we want two G's in order to change equational state and substantial independently, then we have to go again to higher order lattices, or something like this. But please don't be fooled. This lattice is only used for the force computation. So the Lattice Boltzmann population would still live in the first shell, or belt we call it, because steel is an isothermal fluid. And this lattice is only used for the force computation, which is much easier. So we don't need to store the distribution function on 25 lattices. So this is what we call the two-belt model. And typically what we do in the two-belt model, here we have the Shan-Shan attraction. And on the second shell we have repulsion instead. Why do we do that? Well, that's specifically because we wanted, and in fact that's what we are doing today, to model soft glasses where in fact there is the main phenomenon is a slow relaxation. They take a long time to relax the fluid. So the Shan-Shan, the force, the Shan-Shan is like this, right? I have other slides, but it's faster for me to do it on the left one. Now what we're doing is this. Okay? So here I have the standard blue coupling, but here I have a repulsive band. What does it mean? I mean, intuitively, this means that in the Shan-Shan, without the red barrier, if I have a particle falling into this, there is nothing preventing the particles from falling into this, so you say, potential band, which means that I always phase separate, and I always go to configuration where in the end of the day I have just one bubble, because that's the minimal surface condition. Okay? And in a soft glass, you would have, we would like to see a situation where you have many bubbles and the system goes into metastable state, which can last longer and longer. So to generate many bubbles, this is very effective because this means that I have nice movies, but not here. If, say, a particle comes with this energy, it will be bounced back, and so it will not be attracted by the big bubble. So what you say in the movies, for instance, that you have a small bubble here, and in the Shan-Shan scenario, the small bubble gets always absorbed by the large bubble. There is nothing, it has to do that because the system badly wants to go to the minimal surface configuration. When you put this little thing here, and again, it's a minor change, very often you see that the small bubble goes close to the large one, but then it goes back. So it lives much longer. In the end, if you wait long enough, it will always be the same state, but it might take the age of the universe to get here, right? So again, by just playing this trick, we could really study problems which are much more complicated than just phase separation. And this is a typical situation. So this is a two fluid, by the way, but in this trick. So as I said before, this is a fluid A, and where you see fluid A, fluid B is basically zero because they are mutually repelling. And this interaction can generate very, very fancy things that you would never anticipate from the equation. We have really to run and see. What we have noticed is that the system is forming cages, like in a glass, in a way, right? And so fluid A, fluid B, fluid A again, and these cages basically stop the system. And essentially, this is an old picture, but essentially this little line here tells you the fluidity of the system. When this is flat here, means that the system is just blocked. This system at the end, if you wait the age of the universe, or maybe 1,000 age of the universe, will still go into a single boundary. Right? But it will take such a long time that you don't see it. And that's a typical metastable state. So we measure a lot of quantities here. This is not just beautiful colors, they are not that beautiful either. But I can promise, I mean, they passed enough, and we were amazed with Roberto. These are the simulations that Roberto wants to do by himself. Don't take the fun away from it. And Roberto Benz is a very senior, he's the inventor of stochastic resonance. He writes the code, and he doesn't want to have any help, because otherwise you take the fun away from him. Okay? Which is remarkable for a man which is not exactly extremely young anymore. Okay? So the nice thing is just like kind of earthquake, that if you wait, these are 3.5 million times that actually. Every now and then the system wakes up, the belt is broken, and the fluid starts to flow again. So the rheology of this object is extremely complicated, but it seems to provide quantitative, in fact, information, which now we are in the process of comparing with people who are doing emulsion and forms in real life. And that, frankly speaking, I would say is a typical example where I really wouldn't know how to use any Navier-Stokes like code. You don't even know what the equations are. So we derive the asymptotic of our model, we come up with equation, and some pieces of this equation we can recognize, but some other, I mean, we try to map, for instance, this into the Landau-Ginzburg model, and then we ran the Landau-Ginzburg equation, but something is similar, but the nonlinear rheology is not there. And lately we understand, but this is really very fresh, it's not for a didactical purpose. We realized that, as I said yesterday, when two interfaces come very near to each other, if you have the right disjoining pressure, which means the disjoining pressure is positive, so that the two interfaces repel, then these states can be blocked, otherwise they merge. And this ingredient is just crucial to the nonlinear rheology. But this is just front-end research. You don't need to be concerned with that. All I'm saying is that by doing this extension, which in principle we wanted to do just to have surface tension and the equational state independent, then you realize that you can do really much more. So now we are adding very strongly to the direction of doing foam and emulsions. The standard Shenzhen can be I have been using standard Shenzhen for problems like capillary filling, for instance. We have European probes to do that. Capillary filling, I think you know what it is. You have a droplet here, pipette, and then you want to see how the fluid moves into the gas or the vapor phase as a function of various parameters, and there are asymptotic theories, etc., etc. But from the practical point of view, people want to know if you corrugate the surface or either chemically or geometrically, how you would in fact possibly speed up the flow. So it's rather pretty technological, but pretty interesting as well, because the interaction of the fluid with the surface is again something which is not very well known. And if you try to do that with molecular dynamics, you just do a little piece of it. If you try to do it with Navier-Stokes, it's arguable what are you using as a boundary condition. So again, that's the typical middle ground. Lattice Boltzmann really can pick up the best of the two worlds. And for that we use Shenzhen. And there are many, many other applications. I mean, I have specific seminars for that, but I just wanted to give you a flavor. Since we don't have much time, let me move very swiftly into other major mainstreams. Shenzhen is easy. This is not easy anymore. People thought back in, more than 10 years ago, particularly China Lab in Florida State, that Lattice Boltzmann could have been used to do colloids, which is to say we have, say, particle suspension, micrometers, floating into a solid. This could be, say, water. So the idea is that you would use Lattice Boltzmann to solve for the solvent and put some object floated into the system. Okay? So here there has to be a good scale separation between effective molecular motion of the water and the colloid motion. And so but you have to put other ingredient, which is the fluctuation induced on the colloid by the molecules if you go to nanoscale. So this is technical, it's not easy. These papers are not easy at all, and coding is not easy at all. So basically what it does, if you have a solid particle like this, which is moving, is just basically counting, and this is a lattice side inside the colloid. You have to really do the bookkeeping and see who is interacting with whom. So for instance, here the blue arrow has to collide. It's a moving boundary condition. So you have to make a collision between this and this, taking into account, however, that the colloid is cutting through this lattice side. So there is a geometrical weight into this. This is not fun. And if you have to do it in 3D, it's a little less fun. And so the mathematical procedure is well defined. You have to do a boundary. If this was a simple boundary, it would just reflect. So you would say the red arrow is equal to the blue arrow, and when you move, tack, they exchange the situation, and that would generate a sort of zero velocity condition on the boundary. But since this is moving, and since you have to take into account the rotational motion, etc., there are many kinematic and dynamic corrections to this rule, plus geometrical corrections due to this. So the bookkeeping is not easy. Nevertheless, this is very popular, especially in chemical engineering context. And let me tell you again what some of the major problems are. One of the problems that is the solid is much different density than the fluid. You have a problem when you uncover or cover a lattice side. What do I mean? If I am a colloid, the yellow colloid at time t will move to a blue position, so there will be a side which was solid within the yellow, and all of a sudden it becomes fluid because the colloid has moved over. So there is a change in ID. Solid fluid has to be, solid side has to become a fluid side, and there will be covert sides which were fluid on the yellow configuration, and they become solid in the blue. Now, doing this ID change in a single time step generates big pressure kicks. Sometimes they go away, sometimes they don't, so the thing is not easy. So what I call the transmutation policy, how you change ID, again, it's extremely technical work. There are several possibilities. I cannot read this paper easily. But basically the idea is to do the transmutation in several time steps, not just one. Smooth down the kick. And another problem is, of course, near contacts. What happens when two colloids get below, in fact, and here, as you know, there is a lot of very interesting physics, and this physics is totally screwed up if you don't. I don't think we still know what to do with that. So Tony Ladd was proposing again Greek refinement, substep, but these things typically tend to be complicated. So the big advantage for the colloid, so this is not simple anymore, but the advantage is that it's significant, that depends on the parameter. But you know that if you have a situation like this, and you have a solvent aside, the tool of the trade is called Brownian dynamics. And Brownian dynamics basically works like this. It generates, we know that physically, since there is a fluid inside, this generates a vorticity pattern into the fluid, and through the vortices, the colloids see each other through long-range interactions, almost like a gravitational interaction, not really. So basically, you generate a problem which has end-to-end coupling. So each colloid sees every other colloid with an interaction which goes down with some power of the distance. So you have huge matrices and things like this, and this calculation typically at best scale like the square of the number of colloids. In Lattice Boltzmann, the policy is completely different. We still stick to locality, so the interaction between this colloid and this colloid, which is mediated by the fluid, is explicitly resolved. We do that through collisions. This colloid will collide with the fluid, there will be a change in the momentum of the fluid, and this change will carry over to the other colloids, step by step. So the complexity of Lattice Boltzmann is linear in the number of colloids. Of course, the time step is much smaller. So the question is again, your choice. Do you want an n-squared calculation with large step, or you want an n calculation with small step? I take the second on a blind date for sure, especially parallel. And in fact, if you go into the literature, now you see simulation of colloidal flows with a number, with, well, ourselves, we did the aerodynamic simulation with similar policies with 200 million particles, final size particle, which you can't even think of that in thermodynamics. Okay? So again, here you say, there are limitations, the time step is very small, and blah, 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 but still, I mean, you have a potential gain which is really substantial. You are talking orders of magnitude, 2 orders of magnitude in the number of colors that you can choose. So people have used that for many purposes, like the charge colors. I mean, I'm not an expert of this, but I think basically this is of interest for biological applications. One thing which I want to point out, just in case some of you is interested in going into that series, there is recent work by Enrico Maximoni, who is basically a guy coming from molecular dynamics, and just found a way of dealing with this problem, which in my opinion is very valuable and very promising. Instead of doing hardcore collisions like blood, he basically fills up, generates the colloid as a collection, eventually, of spheres. And this sphere has like smooth particle. Some of you might have heard of smooth particle hydrodynamics, which is a technique used in mostly in astrophysics. But essentially, these are smooth particles, and they interact with each other through some soft potential. Again, this is technical, but the advantage is that you no longer have any bookkeeping like Lewis colliding with you. There is a list, in fact, of interactions. So each particle has a list of particles which interact with it, but basically you borrow the techniques, the standard techniques of molecular dynamics, and this has much less problems when you cover all fluid cells. So it's very technical, so there is no point of even trying to go deeper than that. But just in case some of you is interested in that, I strongly recommend this paper by Simone. Okay? This is very technical. Yeah. Another advantage that, of course, we are not limited to spheres. You can do this size, you can change the shape of the interacting part. And that is the paper I was referring to. This is red cells moving into a shear flow. And the final thing I want to mention, which we're running out of time actually, is the fluctuating Lattice Boltzmann, which is to say what you have to do when you start to really go into the realm of molecular dynamics, but you want to do molecular dynamics kind of calculation on much longer time scales. You know that the time scale is a major problem, especially for biological applications. There is a gap in space, but the time gap is much bigger. So if you have a method which can be relatively accurate and march in larger time step than molecular dynamics, people will hear it. So if suppose now you know, or you're supposed to know that there are basically 30 molecules in an nanometer cube. So if you bring Lattice Boltzmann down to delta x 1 nanometer, which is a typical delta x when you put Lattice Boltzmann into the nanoworld, then you might argue that delta n over n, delta n should be the square root of n, so here it's a sensible fluctuation, square root of 30 is fine. And if you go sub-nanometer, then you are in a situation that that kind of a range is 1, so you're wildly fluctuating. How could you possibly use a smooth kinetic distribution? Okay? So, nevertheless, this is space. But if you accept that, in fact, the Boltzmann distribution would be a time average as well, then things are more edible. So, there are applications where Lattice Boltzmann goes to nanometer, or even below the nanometer. When you do that, that's what we did mostly in Harvard about 5 years ago. And here the credit for this method should go to Doomweg. Well, it's not here, it's another. Doomweg was in Max Planck in Mainz. So essentially what you do, you put the lattice Boltzmann on the usual lattice, and then you move, for instance, a polymer. Ideally that should be DNA, but it's never DNA because the interaction are not chemically specific. And what you do, basically, you move the polymer according to Langevin dynamics, which means that P is the particle, so that labels the monomer around the chain. And this particle moves according to equation of motion where you have the friction with the fluid. So UP is the velocity of the fluid at position P, so the red arrow. But the fluid lives on the lattice, so you have to interpolate inside the cell. So this is friction. There is random noise, which is the fluctuation due to the fact that you are nanometric. And there are, of course, the conservative interactions, the potential interaction between the particle and particle. So this is pure molecular. So by doing that, that's the way we did the DNA translocation problems. You can just study the motion of biopolymer into nanoconfined fluids, and so that's a very interesting application. And there again, our Holder myth comes to it's helpful because this is the one we saw early on in the lecture. I call it F tilde because this is a fluctuating force. And the fluctuating force you treat mechanically just like any other force. You have to know how mass and fluctuation contribute to the mass, the momentum, and to the momentum flux, and eventually the ghosts. And I can tell you that as far as this application is concerned, the crucial thing is the momentum flux. This is Landau-Lifshitz fluctuating hydrodynamics. If you go into the book, you see that the way they treat the problem of fluctuation is by allowing the stress tensor to have a fluctuating component, and you have to make sure that this fluctuation component is obeying the standard constraint of fluctuating hydrodynamics, namely the so-called fluctuation dissipation theorem. So what you do basically, you draw random numbers and you plug into the expression of the force, as I show you today. And it turns out, this is curiosity, that if you want to be quantitatively correct, at the nanoscale you have to put the fluctuation also into the ghosts. That's very bad. That's probably the only application I know of where the ghost really cannot be the black. Otherwise, this fluctuation dissipation theorem would not alter the smallest scale. It's very nice one by Mike Cates and Ronjoy Adhikari, where they show that if you neglect these, the smallest scale will break the fluctuation dissipation theorem. So again, this is rather technical, but it's a very important application because here we are really with this type of problems with biopolymers, saying in nanoconfined fluids, there's tons of application in biology. So this is called the fluctuating lattice Boltzmann, and I wouldn't say it is a major mainstream, but it's certainly picking up quite fast. And again, here we would like to have the fluctuation can break the system. The numerics is delicate because basically, it's a stochastic differential equation. So, and the way we do it, we just put a random number and then multiply by delta t. And if you do that, you kill the scheme very easily. So the time march here has to be a little bit smarter than what I showed. So the way we deal with the stochastic source, I would say, still suboptimal. There is work to be done. So fluctuating lattice Boltzmann would break down much more easily than standard lattice. Okay? But the machinery is more or less, I mean, by now you know. I mean, the package is always the same. Stream, collide, and eventually bias. And this bias could be brought, again, into the equilibrium, as I showed you. So with that, I think, any question?
Yes, about the force that we have, no matter if it's fluctuation or principles. I've read somewhere that we can incorporate it in the equilibrium function.
That's what we should.
Yeah, exactly. Or add it here, or do both of them. Also adding here and incorporate it in the.
Yeah, I know that, but I really didn't follow. You can do what you want, but what would be the point of doing both? What would you gain? No, I'm asking because I don't know this point. In general, I mean, but that I didn't show you. If you incorporate, I could show you that you're enhancing the stability, because this is just like having a further diffusion of velocity space, which is moving things out in velocity space, if you incorporate. I'm always much in favor of incorporation because I saw with my eyes that it is more stable. And then I understood why. So what is the point of keeping one part incorporated and the other outside? It's beyond my understanding. So these things are very delicate. It could be that there is one, the way you compute this force can be very delicate. I mean, I gave you the vanilla version. But in reality, the force has to be computed at time t, t+1, and the average. I mean, there are many, many tricks. I mean, that will really take a long, long time. But the way you compute it, you just change a little bit detail on the way you compute, and then the stability of your scheme will really change. So there are at least 3 or 4 different policies to implement external forces. But I mean, the simplest level, either you bias explicitly or you incorporate. If you incorporate, I know for a fact that it's just like having an extra piece which is diffusion of velocity space, so that helps smoothen things out.
It couldn't be more stable if you use both.
I don't see why, but could be. If you want it in the paper, you could distribute it. I don't see why. The real point would be doing the nonlinear thing. I mean, just handling larger forces. That would be a major advance. But again, I don't know how to do that. So handling larger fluctuation, because now it can fluctuate a little bit, but not too much. Okay, so any question with this? I think this is an old. So the various, yeah, these are commented. So basically, the code scales linearly with the number of objects because there is no actual distance. Everything is local and explicit. One thing I forgot to tell you, well, we touched a little bit on that, is that we never solve for the pressure because we never impose the divergence of the velocity field is exactly 0, and this makes that simple. And I think we cover all of this. Small constant, the moving boundary is still in flux. Now, much of the Lattice Boltzmann literature, I must say, I don't read it. It's very good. Most of the papers are on the boundary conditions, big test, which matter for this paper. You cannot dismiss them. It's interesting. I'm more interested, in fact, in exploring the use of Lattice Boltzmann as a tool of discovery. I don't care about second orders. But if I can do a problem that people would have to write a code and take 6 months just to write a code before they see a simple result, what I really like most, if you go with Lattice Boltzmann and say, look, don't trust me too much. But maybe you will get an idea, and you will get it in a week. That's what I like most. But it's a matter of taste. Whereas, no, clearly, especially with the multi-phase, but also the colloid. They have their own method, which worked for 50 years, and they are angry if you, at the beginning, they say, oh, that might be interesting, but after a while, either you show they can be better or not, and they're right. You cannot play around for 10 years saying, oh, looks like I'll show you that you can do better. And doing better in terms of accuracy is not easy, because, as you say, accuracy is not a problem, not a part of strength, but we have other strengths, as I showed. So in the end, always the same: simplicity, power computing, contrast reality. And on that front, I think it's very hard to do much. Okay, so that will be finished, but if you have, the terminal, you will be disappointed about the terminal, right? But we had a private discussion, which was maybe not that satisfactory either. Well, let me see what I have on the terminal, if I can have just 10 extra minutes. I didn't do much thermal calculation myself.
How about this? At this stage, I'll just say that I would like to thank Sauro for this week, where he walked us through a rather involved and developed field, and saved us from reading a lot of other papers.
Including my book.
No. But this is, of course, exactly the point of giving a short course, and you've stimulated a lot of questions, and I think helped
Hopefully
some
collaboration.
people and collaborations, and if people want to stay and ask questions, that would be good. But I do want to thank you for exactly doing all those things for us. So.
It's of course for me to thank, because there is nothing better for a scientist than interacting with people, and young people, and less young people, and so on. And you always learn as well. So it is for me to thank John in the first place, and the organization here, and you for being resilient for the full week. I really enjoyed that, and I'm really grateful for this. Thank you.
So if anyone wants to leave. But I'm going to listen to what you say about thermal problems, because those are of interest.
Well, in fact, I didn't prepare much on that, and because I didn't really work much on terminal, and I'm afraid that what I have here is not really a complete list of the several methods which are used to compute thermal force. Well, let me try. I don't even remember what's in here, but let me try just to briefly give just an idea. So the problem, I think I made clear in the beginning, that if you want to be serious about thermal, serious means that you want to have an evolution equation for temperature, which is driven by convergence of a heat flux, and we want to be quantitative. The lattices we have been using all over for isothermal flow do not work anymore, because you need 6 orders. 6 order equilibria are very easy to write down. Again, our limit serves very well our purposes, so here I write it in a different way. Beta is 1 over sound speed square, and this is just a shorthand for this notation. Ui is first order, is a sort of dipole interaction with velocity space. Q is Q, the quadrupole, and then we have to have the exponent. So we have to have limit 3, and that's very easy to write down, except that you have to do that in a lattice, which is 6 order. So the first thing people did in the early day, in 2 dimensions, without they constructed equilibrium which looked much less elegant than this. They put a lot of parameters, okay, because at that time, I'm talking the 90s, it was not yet recognized that there is such a clean limit expansion. And so they meshed the parameter in equilibrium so that they would recover the equation of Navier-Stokes Fourier. Okay. I think the first work was by Francis Alexander in Boston. And they computed thermal, wet, and simple situation. Now, the problem with the thermal is that and I think this is only partially solved, as far as I understand, that this beta is basically 1 over t, right? So So in the standard lattice Boltzmann, I always told you T is C sound squared, which is a lattice constant. But if T is T is not a constant anymore. In the early days, as soon as you try to put something which is not a constant with this equilibrium, boom, you leave it. Why? Nobody really knows, except that Udon Chen and Peter Callen pointed to me that the entropic lattice Boltzmann, which I talked about yesterday, when you extend it to, I mean, there is no H theorem which would work for a lattice Boltzmann for a thermal lattice Boltzmann. So that somehow is the situation just opposite to what happened to us back then. We were pushing the viscosity, the famous 1.8 by the Bentley constant, in a ground, in a no-fly region, which in fact was forgiven. Here is totally forgiven. And I might be wrong, but I think as we are speaking, I don't think there is any method where you can just plug the actual temperature and stay away from this particular. So what people did, the way you integrate the temperature field can change a lot. I mean, you could use a standard lattice Boltzmann, you are no lattice, so you forget to buy a lot of the lattice. You integrate T, finite differences. But as soon as you try to put the actual T inside here, it goes up. So people use constant temperature equilibrium. Eventually they put an average, and but not the actual value. Now, why is that? I think it's because of the lack of an HT. Let me see. This is always the same story, so these are the lattices that I'm using. Let me see if okay. I would just comment, we were discussing that yesterday with you. One smart paper, it's almost 10 years old, and as far as I can judge, this is the method which is mostly used. So let me just give you an idea. This is an outside data. So they said, well, there is this problem of going to the higher order lattice. Why don't we do what in interpolation theory thing is called Lagrange versus Sergei? Instead of putting, if I have a resolution like this, instead of doubling resolution, I can stay with the same resolution but have not only the function, but having the function and its derivative, so to say. So just put in more information on the same lattice. So they propose a so-called double distribution, which is to say we have F for the particles, and they define G as a sort of local energy density. Okay? You can always do that. Of course, G and F are one-to-one related, but the advantage is that formally, if I treat G as, say, the phonons, okay, so that their density would be my temperature and their flux would be heat flux, then I can construct two equations, which in principle are photocopies, but in practice they are not photocopies, so they have equilibrium which are just the same, except that instead of having rho, I have rho T, and instead of having U, I have the flux of, I have the momentum, sorry, the heat flux, which is going to happen. So for some magic, it turns out this double distribution method is more stable, and most of the applications I see around today are done this way. So I really not. Then again, there are many variants, and I'm not really following very much. Ourselves, we have a paper where we show that if you have a thermal flow, in fact, you don't have to shift just U, but you have to shift the temperature as well. But that's again highly technical. I would say that by and large, there are two main avenues. Either you accept that you have to work on a lattice which has double links, and there are many families of possibilities. Some people use octagons, for instance. I'm not sure I'm able to. How would I do? They have lattices like this, okay? And you can show that an octagon has enough symmetry for the 6 of the tensor, except that you have a little problem here because the octagon is not space filling, and so they have again to interpolate. This method has not been very popular. So the two most popular options are either I go sixth order or more on double lattices, or I just stay with it, and instead of putting F, I put F and G. And this F and G appears to be significant in most days. Then of course you have to ask yourself a few practical questions, which I always ask as a referee. Why are you willing to pay such a huge price? In 3D you have 19 plus 19 population just to integrate the energy. Why aren't you happy with the so-called hybrid solution? Hybrid solution is lattice Boltzmann is for the fluid only, temperature with any other one, which in fact is the third option. I see more and more hybrid calculation, but lattice Boltzmann is left where you know that it really works well and you don't venture away from that. I cannot tell you, frankly speaking, which one is best, but I can tell you as a referee that people don't think much of that. So, double distribution, have you ever thought that your memory overburden, and the memory, here I give you technicality which is very important. The memory overburden in lattice Boltzmann, in 2D you don't have, but in 3D you should. Because it's not that you're just doubling your memory, but this is because since you have many arrays, the real performance limit in lattice Boltzmann is how much it takes to fetch your data and bring it to the CPU. It's the data access, really, which limits the performance. So you know that when you have a long list of arrays, the so-called data locality in computer science gets, I don't know whether I'm to tell you, but you should definitely be aware of that if you do 3D simulation. When you know that when you access an array, a long array, AGK, right? In Fortran, you will store it along I, so this would be I1 to the next, then you would have the next, so in fact, I1 and X, and this would be J1, K1, then you would have J2, K1, so in a long array. Now, when you access K plus 1, you have to do that, because the computer memory is one dimension. And doing that, it means that if you have brought into your local cache, your local memory, just this first part of the array, you have to download it and refetch. This thing is what is costing you a lot of it. So, by the time you double a big array, or a series of arrays, considering you have 19 three-dimensional array, these so-called cache misses become much more frequent, and that can be a big penalty. So I'm not sure at all that it is convenient to use two double distribution rather than doing an hybrid calculation. I don't know. But I see that people don't ask the question themselves, and they should.
So what you said in the beginning, to using another method, so you would use the output from LB to compute the velocity field and then solve the induction diffusion equation for the temperature.
Right. So
And then
basically
you
that-
just prescribe beta for each time step.
Exactly.
And
So, option one, go to higher order lattice, full lattice Boltzmann, and then you have a lot of discrete population, right? Second option is standard lattices, which in 3D means at least 19, but double, F and Z. Third option is standard NB for F plus, say, finite differences for T. But T, so F gives the velocity to this should restitute T, it does, but you don't put T as a function of X and time into the local equivalent because you crash the scheme. Eventually you give an average and there is some T squeezing. What I'm saying here is different. I'm saying, and as far as I can judge, but I'm not sure, this is the most popular line, this comes second, and I don't see much of it. But again, not that I know every paper, not at all. All I'm saying is that when you do that, here you are basically, you have 33 arrays, 33 and X and Y and Z arrays, okay? And here you have 19 plus 2, okay? So you say, okay, it's a factor of 2. Well, factor of 2 in you have memory enough. But it's not the factor in itself, it's the fact that the cache misses here will be much more significant than here. So you have to ask yourself whether you are really gaining. And this is not obvious to me. One point which I always suggest as a referee to check is the size of the timestamp here. Because it could be, but I've not seen any measurement of that. That by using Lattice Boltzmann, indeed, since I'm always working with this very nice feature that C delta T is equal to delta X, that brings me many benefits. Some of them I've illustrated, not all of them. And, but it's just like working at Courant 1, in a way. And normal explicit finite difference scheme would have much smaller timestamps. So I always ask to compare someone, at least to get the flavor. I think Boltzmann, if Boltzmann is an advantage, it's because of this. Otherwise, I would not use this. Why should we use 19 arrays just so we don't start? But this can, I mean, we have other fields, so I cannot really carry over. But when we do, for instance, finite volume lattice Boltzmann, right? And you lose this beautiful property, delta T goes 10 to minus 3, very easily, instead of 1. Okay? So I don't know what the delta T of the hybrid schemes is, but I suspect if delta T goes, say, to, instead of being 1 goes to 1/10 or 100th, then there is a reason to do that. But people don't ask this question. So they go straight, that is necessary.
Would you recommend the third method even if one is solving for a turbulent flow? Because I mean, like one, say if one is actually doing a DNS, then the finite difference part would become a lot more complicated.
The final difference part for turbulent flow would be miserable. I mean, we would not know.
So the coupling would be out of question.
Can you do turbulence with finite difference? I don't think so.
Yes.
Yes? Well, but the temperature is probably much less, does not require the same amount of resolution as
We
the
actually
flow.
don't do it with temperature, we do it with entropy.
With?
With entropy.
Entropy.
Well, okay. But maybe the entropy is more close to a passive scalar than the fluid. So maybe you don't need the same resolution for the fluid as for the temperature. If you try to do turbulence with a finite difference method, and you compare with spectral, there is no comparison whatsoever. So in that sense, Lattice Boltzmann is way better because of the conservation. For temperature, I don't know. But all I'm saying is that things are never so simple. When I see people blindly going for the two distribution in 3D, in 2D you don't mind. I always ask, why are you using those? It is irrational.
But you can probably minimize cache misses by coding in a different way, doing in chunks. And also caches are getting bigger
You know,
with time.
when I was at IBM, you know how those things started for me? That's really funny. It started as an exercise of assembler language on IBM machines. My boss came to me, saw a PRL on Tommaso Toffoli, you might know him, okay? Cellular automata for Navier-Stokes equations. But look at this, why don't you try to code this while you're, I had to take a course in assembly language. That's the way the thing started for me. So I know about computing tricks, right? And I love them. Now I don't have time anymore. But I know that there are definitely, I mean, making your code working properly, parallel code, is impossible unless you don't code move and collide. You do any sort of prefetching and just to avoid memory, minimize memory access. That's really the trick. And yeah, there are many different. When you program hard, you don't do move and collide, you do them together. It's called fused lattice bolts. They merge. And if you do it on GPU machines, the same. So it's a job in itself. I have a colleague of mine who's really top in the class in that. He's perfect. So I don't do that anymore, but I know what's going on. He is really on top of that very much. So all I'm saying is that, yeah, when we say 3D, parallel, etc., I hope I didn't give you the sensation that this comes for free. I mean, when you get a Linux without over 2 million cores, it's because people did hard work to do it. I mean, if you just program vanilla, no way. But the reason is cache. Boltzmann. And typically what you see in Lattice Boltzmann is like you have parallel speed up, but you get only a fraction of the peak of the machine, because just on a single core you get a fraction because of the cache misses. See what I mean? If I run on one machine which gives me, say, 1 gigaflop single processor, I get, say, 200 megaflops, so 20%. Then I can scale up this 20% to 2 million machines, but it's still only 20%. It's not just like that. So basically, when you have a large data set, you are always, in 3 dimensions, you are always out of cache. And sometimes parallel computing helps because each single computer gets less things to compute, and so you should super linear speed up. So that very clearly. You have, say, 1,000 cores, and it runs more than 1,000 times faster because each of them has less memory to access. I mean, so coding Lattice Boltzmann in hardcore 3D application is a professional job in itself, for sure.
Should we take it to lunch?
But again, I mean, on the terminal I'm not really very knowledgeable. So I think that what I said is by and large correct. But I don't know the case. Maybe there are new papers coming out. But certainly it's much less developed than Istituto. Way less. Okay, so thank you again.